Good morning, class. Today we're going to be learning Lesson 7.8 and factoring polynomials completely. Today you will learn to factor the polynomials by grouping, to factor them completely, and to use factoring to solve real-life problems. So we've used distributive property to factor out a greatest common monomial from a polynomial. Sometimes you can factor out a common binomial. You may be able to use the distributive property to factor polynomials with 4 terms as described below. When factoring by grouping, to factor a polynomial with 4 terms, group the terms into pairs. We're going to be looking for some common factors. So factor the GCF out of each pair of terms, look for and factor out the common binomial factor. This process is called factoring by grouping. So remember that addition is commutative, but in a polynomial, the sign in front of the number represents a number. So if you start moving things around and it was behind a minus sign, make sure that you make that term negative and in its place put a plus sign between them. So we'll get started and do a couple examples. So for the very first one, we're going to factor by grouping. So we're going to look for some common terms. There's 4 terms. And let's see here. The first 2 terms, a cubed plus 3a squared, we could probably factor out the a squared. So we'll group these 2 together, and then we'll group these 2 together. Okay, so in the first group, we know we can factor out an a squared. A cubed divided by a squared, what we're leaving behind is a 1a, okay? And then since we factored out the a squared from the next term, we're leaving behind that plus 3. Notice the next binomial is pretty much completely factored. There's no common factors between the 2, so it's kind of like we're factoring out a 1. And I like to go ahead and write it. You don't have to, but sometimes in keeping track, it'll be a little easier at this early stage. All right, now we're going to look at these 2 terms that we were left with, and we see that they each have a factor of a plus 3. That's a common binomial factor. So we can factor out that common binomial factor right here, and write it 1 time. And what was left is basically this, leading factor that we had already previously factored out. So we have our a squared, and that's a positive 1, so plus 1. So this was factoring by grouping. So we grouped them together, looked for the common factors, looked for a common binomial factor, factored that out, and then rewrote what was left. Let's try 2. First, we're going to have to rewrite so that we could group things together, because I can see the first 2 terms, y squared and 2x, do not have a common factor. But the y squared has a common factor with the xy and with the 2y. But if I go ahead and rearrange the terms and rewrite it to be y squared plus, and I'm going to kind of switch these 2 terms right here, 2y plus yx plus 2x. Now I can group these 2 pairs, and in the first pair I will factor out a y, and I'm going to be left with y plus 2. And in the second group I'm going to factor out an x, and again I'm left with a y plus 2. Since that gives me a common binomial factor, I can factor this out. So I would start by writing it in parentheses. Y plus 2 is a common factor to both. What was left after I divided both of those terms was the y plus the x. So now I've factored it completely. You could always go back and check in the end. If you FOIL your 2 binomials, you should come back to your original polynomial. Okay, so what it means to factor something completely, and I think this might have been where the confusion was coming in a little bit with our 7.6. We would say that a polynomial is not factored completely if there is still some part of it that can be factored. So we need to take it down to its like, I guess when we start thinking about breaking things up into its smallest parts, one way mathematically to describe it would be like its prime factors in a way. Like if you can't factor anything else out, right, what you've left with is either a prime number or a prime coefficient or something that their greatest common factor is 1. So I was a little flexible when we were learning how to do 7.6 because you were also just learning the skill of factoring. However, today you're really going to see why it's so important that we first factor out those common factors, and I think that as you progress you'll understand this. So we've seen that the polynomial x squared minus 1 can be factored as x plus 1 and x minus 1. That is the difference of two squares. This polynomial is factorinomial, but look at this polynomial, x squared plus 1. It cannot be written as a product of polynomials with integer coefficients, so it is unfactorable. So in this case, this could be a binomial factor of one of our polynomials. So sometimes you'll get down and you might even be left with an unfactorable trinomial. So I'm going to kind of point you in the direction of looking at those examples as well. But a factorable polynomial with integer coefficients is factored completely when it is written as a product of unfactorable polynomials with integer coefficients. So this is the key that we were missing, the piece of information we didn't have when we did 7.6. And we need to be very careful that we've factored everything completely from this point forward. So this is going to be our guideline summary, and this is in your book. To factor completely, you should try each of these steps. So if you first try something and it doesn't work, then try another method. So first we're going to either factor out the greatest common monomial factor. As in the example, we can factor out a 3x. For 2, look for the difference of two squares or a perfect square trinomial. That is your 7.7 lesson, so you can go back and review those notes as well, but you're kind of undoing the pattern from when you were working forward. For 3, factor a trinomial in the form ax squared plus bx plus c into a product of binomial factors. Okay, and 4, factor with 4 terms by grouping. So we're going to apply some of these. So let's factor completely. So when I look at this binomial, I look to see if there is anything that can be factored out. And in 3x cubed minus 12x, I know that I can factor out a 3x. So divide each term by 3x. 3x cubed divided by 3x leaves me with x squared. 12x divided by 3x leaves me with 4. All right? And you might think that you're done, but don't forget to look a little further. If you look at this x squared minus 4, that's the difference of two squares, because 4 is a perfect square. So we could factor completely, and if you follow the pattern, the difference of two squares means that we're just going to find the square root of the 4, and we're going to write it as, x plus 2 and x minus 2. So we'll keep the 3x on the outside, and then we'll break up this that can be factored more completely into x plus 2, x minus 2. Now we can say that we have factored completely because we're looking for patterns and we're looking to, again, write it or simplify it even further. For number 4 in the middle, when I look at the 3 terms, I know that they all have a common factor of 2y. So I'm going to kind of work a little bit lower here. I'm going to bring out the 2y. I'm going to change colors too so you don't get them mixed up here. So if I factor out the 2y, I'll be left with y squared minus 6y and plus 9. Whenever my constant term is a square, I could always look to see if there is a pattern. And remember, the pattern was that you could, like the middle term was, minus 2ab. So if I could take that middle term and divide it by 2, and it is one of the factors of the square, then I know that I have a pattern. So the square root of 9 is 3, and to be positive, it is either both positive or both negative. And if I'm working with 3 and I need a middle term of -6, then both 3's need to be negative. So my completely factored form would be y minus 3 times y minus 3. I could then simplify and write it back with the exponent of 2. Okay? And finally, looking at number 5, I have m cubed minus 2m minus 8m. The only factor I can pull out is an m. I'm left with m squared minus 2m minus 8. And I'm going to be looking for, and sometimes I show my work like this, right? I'm going to be looking for factors of -8 that would sum to -2, and I know that it's going to be a -4 and a +2, so you could do your factor fish if you want to, or you could, puzzle through it by comparing the products and the sums, the factors and the sums. Okay, so in this form, m times m plus 2 times m plus minus 4, I am factored completely. And I do want to direct your attention to example 2 on page 405. I didn't do an example like this, but sometimes you'll get to the step possibly here where you've pulled out a common factor and the trinomial left behind cannot be factored anymore. So please look at example 2 for an example of when the trinomial is already factored as completely as it can be. Okay, back to some of the equations. So we will complete the process just like we've been doing. We will factor the trinomial part of the equation completely, then we'll solve the equation for the variable. And again, when we start to apply this, some of these we may find, well, these don't even make sense because you can't have negative lengths, but some of them will. So in the situation, so in the first one, 6, this will just give you more practice. Definitely start by factoring out the w. You're left with w squared minus 8w plus 16, and the whole thing is going to equal 0. Again, looking for some of those patterns, I see that 16 is a perfect square. It's positive. So we could have a +4 times a +4, or a -4 times a -4, and since my middle term is a -8, I know that it's the -4. So it saves a lot of time and effort from having to do a factor fish if you just know that it's the product of two squares. Now, since this is an equation, I don't have to go to the next step and write it as w minus 4 and the whole quantity squared, because I'm solving one of these three factors is equal to 0. So either w is equal to 0, w minus 4 is equal to 0, and it is redundant to write that twice. So w equals 0 or w equals 4. So my two roots of this equation are going to be w equals 0 or w equals 4. Again, you don't have to duplicate that 4. All right, looking at 7. X cubed minus 25x equals 0. So let's start by factoring out an x. I am left with x squared minus 25, and that whole thing is equal to 0. So I see a difference of two squares here, so I can rewrite it as x plus 5 times x minus 5, and that whole thing is 0. So again, it makes the factoring a lot easier when you can identify the pattern. So x is equal to 0, x is equal to a -5, or x is equal to 5 would be the roots. So I've just gone ahead and solved them without writing them. Okay, and finally the last one for this page. Let's factor out a c. C squared minus 7c plus 12 equals 0. And now I'm looking for factors of 12 that would sum to a -7. And already 3 and 4 come to mind, and if they're both negative, I can get there. So you'll see that, so c minus 3 times c minus 4, your factoring skills will get better and better the more you do. So we have c is equal to 0, c is equal to 3, or c is equal to 4. So 0, 3, and 4 were the roots of this equation. And now we're going to use this concept of solving the equation so that we can apply it to a rectangular prism. It has a volume of 72 cubic feet. The box has a length of x feet, a width of x minus 1, and a height of x plus 9. Let's find the dimensions. So just going to summarize a few things here. 72 feet cubed. I'm visual. I like to see what I'm working with here. Although that's terrible. Okay, so we'll call this side x, we'll call this side x minus 1, and we'll call this side our x plus 9. That's our height. Okay, so I know that the volume formula is length times width times height. So my 72 would be equal to, and I'm going to have all three things multiplied together. So x times x minus 1 times x plus 9. Okay? When I start to solve these three factors, just like you would do any other thing, take and first the first two factors. So 72 is equal to x squared minus x is going to be multiplied to x plus 9. So we'll get x cubed first. The outer would be 9x squared. The inner is x squared, and the last is 9x. So in simplified form, 72 is equal to x cubed plus 8x squared minus 9x. Now we need to get that equation equal to 0 so that then we could solve it. So if we subtract 72 from both sides, notice that there is no constant term. So we end up with 0 is equal to x cubed plus 8x squared minus 9x minus the 72. We can start a factoring by grouping since we'll have 4 terms. And we'll keep, so remember we were talking about this before, so we'll change this to plus, and then this is going to become negative 9. Okay? So we will first factor the common factor between x cubed and 8x squared. So we will factor out an x. We will be left with x squared, x plus 8. Okay? Now we have a negative 9x in the parentheses minus 72. So negative 9x and negative 72 both have a factor of negative 9. So I'm going to factor out the negative 9. I'll be left with x, and then when you take a negative 72 divided by a negative 9, plus 8. This is working out really well so that I have a common binomial factor of x plus 8. So I'm going to kind of continue up here. So 0 will be equal to, and I have my factors here, x plus 8 is the common factor, and then x squared minus 9. Oh, look at that. That looks like a difference of 2 squares right there. So 0 is equal to x plus 8, and then we'll have x plus 3 and x minus 3, so that x will either equal negative 8, negative 3, or 3. These two can immediately be discarded because you cannot have negative lengths. Okay? So that means if x is equal to 3, I come back over here and I say that my length is 3 feet, my width is 2 feet, and my height is 12 feet.